research on and so on. So that's my basic goal for today. Well, the background was pretty well established, but so that you have an idea, I am a digital signal processing engineer. So I am not a mathematician. I am not an audio engineer, anything like that. I basically gamble with the math, but I am not a mathematician, or I shouldn't, but I do. And I basically build up models for different stuff. Okay? In this case, sound and speech are the most typical applications, but not necessarily, because for me, essentially, radio communication systems, a radar, whatsoever, you could imagine that would have a signal is equally valid as a research, but not for the time I'm here. So actually, just so you have an idea of kind of things in which we work on, these are basically papers from conferences in this year that I co-author. Essentially, first one at ICASP is a shared contribution with actually with Professor Price, with Josh, and actually as well with Mateo, who I guess most of you have experienced before or seen and talked to him before. I happened to be his supervisor at some point in his life, already a PhD. So essentially involved, you have the kind of, well, there are conferences that are international that you certainly know, and there are others, well, actually one that closed a few hours ago, the deadline for submission, the last one, but there are also some in Spain.
Can I see the deeds?
Yes, you can. Oh, you should be sharing.
No, that's fine.
Okay.
You're sharing.
Yes.
But I want to check the microphone.
Okay. I was told you know the tricks about this.
That may be better.
Really?
Yeah.
Yeah, it seems so.
Yes.
It's in the range. Yeah.
Can people online hear better now?
Much better.
Thanks a lot.
Okay.
I should have asked. My fault. The mic is not so good, so maybe you hear better, but some distortion will arise. Anyways, so as said, essentially these are some papers so that you kind of have an idea of what kind of research we do. As said, this is just part of what we do in audio signal processing. There are other branches that we address, or that I specifically address. So to say, essentially, this means that I am not so much interested on sound per se. I am interested in the systems that produce sound, assuming that the kind of info that I can get from those systems is essentially sound. Okay, but sound on itself is not necessarily the thing that most interests me. So actually, I've been working already 15 years in system theory, which basically means how can I extract information about the actual system that produced the sound or whatsoever. And this essentially means characterize it or build a digital model for that, or actually estimate parameters, any kind of thing like that, which allows us essentially to build up virtual models for those components. And those virtual models may go into a DAO if you are playing sounds and synthesizing sounds, or may actually go into a satellite and allow some kind of system to do blah, blah, blah better, so that you have a kind of an idea. But we also play with machine learning and generative models, which I guess we all do by this time. I don't know if there's someone in the audience that does not work with machine learning, but I guess we all do. So part of the work that we do is essentially around learning, but about learning for those systems, which is kind of a peculiar way of learning. I always like to summarize my work in this kind of a neural analysis by synthesis. So essentially, if I can build up a model for the system that maybe it's neural or not, that actually matches the output that that system can have, I've learned something. Okay, and we use this actually not just for speech and sound, but also for clinical pathologies as well, based on speech. So essentially, the model is kind of something like this. I guess it's not surprising for anyone. Essentially, there's kind of an excitation and some parameters that go into the system. So this system, the thing that worries me, there is some radiation or propagation of sound. Eventually, hopefully, there will be a wave, and probably we will record that and do things with that. I don't know whether you work in synthesis or you classify, if you focus on the audio or you actually don't focus so much on the sound, but go for music. Essentially, as said, my goal is essentially the system. So if I had to summarize kind of what we do, essentially the research question that you have there would kind of kind of summarizes our work. What can we learn about the system that produced the waveform from studying this wave? But that's essentially kind of the goal for our whole research group. Okay, so it's kind of a not so easy question to solve. So I would rephrase this in this way, which is actually the topic for today. Can we actually build control paths for simpler problems to produce expressive sound producing systems? So the key idea here is we define paths for learning. By the way, could you all raise your hands if you have used machine learning or you frequently use machine learning in your research? Okay. Then everything is okay. Yes, just in case it is not. So since you are younger than me, most likely to have not experienced what I will showing you now, but essentially for 20 years, people were playing around this idea. We have a system under test and we want to evaluate it. Let's build some math so that I can actually excite the system, get its output, and based on these two, hopefully build up a mathematical model for this. So these days, the function that actually is expected to reproduce that model would essentially be anything. Okay. These days, which we are neural, most likely you are thinking about, I don't know, convolutional neural networks or whatsoever, or more complicated models. But essentially, since almost 1 century ago, we evaluate some kind of loss. We see how that loss implies that our model works or doesn't work, and we feed that back into our loop. And that's essentially the way in which we learn to build up a digital model for a system. But no big deal here. Now, this is tricky, actually, because once you decided to do this, you've made some key decisions, which mathematicians actually hate and we tend to ignore. But essentially, at this point, you would have decided what's n. N being the length of your sequence. That's a problem. Deciding exactly what is the length of the sequences that we should evaluate, not because the neural model will have problems to evaluate that, but because the information may not be there if you do not get enough time. Simple as that. Now, there are other things as well, which is actually the sampling frequency. Actually, we wrote a paper some years ago on how the heck should we get the right numbers to do this. And basically, so that you know, we won't like the results, because essentially we need more time and more sampling frequency. And 99% of your time, you use a data set with a fixed data set and fixed sampling rate. So not the best, but just for you to know, while we get to this point, we have already made some decisions. So based on this function, any of you that have experienced these Volterra or Wiener systems? Yes. Why? Because you were requested to, because you had to, because there were no other way. I wasn't expecting 2 people in the audience to say yeah. So yeah, you did and you did. So what for? If you remember, if you don't, it's okay. Okay. It's related. It's directly related. In this case, the Wiener system is kind of a generalization from the Volterra ones. If you haven't heard, essentially it's a generalization of the impulse response, so that you can actually build nonlinear systems based on a generalization of this idea. Essentially, not so complicated math, but a lot of numbers, things becoming quite large, quite big, quite difficult to handle. So that you know, this is essentially first 20th century, so not quite recent. The Wiener systems are essentially 20 years later, so it's still 1930s, so some time ago, actually 1 century almost ago, but essentially we still use them. And we use them because they are quite procedural, which I guess it's a word you already know. So essentially you build that math. It has relatively simple operations that can run quite real time, awesome thing to do. Now you don't use it, and you don't use it for sound these days. We ought to, but now we don't, because essentially the kind of representations that we have are not so expressive, first, and second, the learning process is a mess. Please correct me if I am wrong. All of you that are using machine learning are using kind of gradient descent stuff, stochastic gradient descent, Adam optimizer. Do you all? Yeah. Have you ever thought about why you are using stochastic gradient descent if you are, or why you're using Adam? Okay. Go. Kind of makes sense, right? So it's true, it can actually trace local minima. Now, should that be the best? Have you ever been concerned, really, okay, I don't mean in a paper, a few lines, have you really been concerned about the fact that your solution is not so good because your problem is non-convex, and you actually know, you absolutely know that your result is not good? Have you? It does happen, okay? And specifically, it happens a lot in the kind of research that I do, where I essentially have an inverse problem. I want to estimate a system from its output, and that essentially is an ill-posed problem. So that's definitely not so easy. So essentially, it's typically non-convex. I would like to look for a procedure that I can prove positively that can handle this local minima and actually go for the global minimum. And that's exactly what we have. Essentially. Additionally, I guess you all know that in standard machine learning, you basically have no control of the learning process. So you basically go with the Adam and fingers crossed, essentially. Let's go. Hopefully, that's a problem, okay? Essentially, because there are things that will happen during that training that if you look deeper into those, there are things we could do. Essentially, just to summarize, from this 1 century ago, we had of the neural networks or their variants. We also have quite a lot of research being done on more procedural models being connected to neural networks, which for what I know here at C4DM, you have quite a few papers on this, even us with people here, so quite interesting. And I guess you all heard about DDSP, right? Have you not? Yeah. So if you had to summarize what DDSP is, what would you say? Plain words, no mathematical, no mathematician, please don't be afraid. Okay, I'm happy with that. Now, differentiable in what sense? Slightly mathematician. Slightly mathematical. So typically, you have your functions and you differentiate and done. Okay, so it's kind of differentiating a function. Yes, gradients of functions, right? Now, how would this change if instead of differentiating the functions, I differentiated the operators? Because if you think of a linear system, essentially what you have is a linear operator that is describing you the convolution, right? What you differentiate typically is the impulse response or the parameters of the impulse response. What would happen if I actually differentiate this notion of the convolution? That's kind of what we are going to suggest you to do. And by the way, since you mentioned this idea of differentiable and continuous, if you haven't heard of this word modifiers, have you? Are we all engineers or kind of? Yes, no, yes, kind of, let's say yes. You know these situations where you kind of get a result and you just add a little bit more so that it is not zero when everything works, so everything is continuous? Now there's a mathematical word for that, 2026, modifier. So you can have a layer within your models that is called like that essentially can handle this idea. So essentially, everything is differentiable in your way, in the standard way. What I'm going to describe to you is what we do that makes things a little bit slightly different, differentiable. So essentially, I'll do my best, but we have some kind of nonlinear problem, whatever that means. We've got some parameters theta, parameters for the system. So theta is what I want. And I essentially have an excitation and a reference time. So in standard typical machine learning, standard problem, no big deals, nothing new. You essentially get your data. You will define some kind of metric that you want to evaluate. And then you will basically decide how complex your model might be, which is essentially M. So how good your approximation is going to be. If you want to put it in terms of neural networks, how many layers or how many coefficients or how many parameters you want to compute. And you also have this idea of K of wait, you just wait. How many steps? I don't really know. Will this converge? What does exactly converge mean? I mean, just goes down, it kind of seems flat. Correct me if I'm wrong, but this is essentially what we all do. So 99% of us essentially focus on just one problem and then approximate the solution. Please note the words, focus on one problem and approximate a solution. Okay. Now, Essentially, this means that when we have a machine learning problem, we formulate it. So we have a task, we have some data, we have a metric that we define. We basically pick those, hopefully in a kind of smart way. And then we hope for the gradient descent or a stochastic gradient descent of the atom or whatsoever to work. Let me ask you something. What do you do when those do not work? Do they always work for you? No, what's no? So it simply doesn't work, simply crashes, kind of vanishing gradients, kind of, what happens to you? How do you know that this thing is not working? And even most importantly, what do you do when that happens? Oh, remove one. Yeah. Actually, in some applications, in communication systems, this kind of machine learning is not standard yet. So actually, that's 99% of the researchers, one up, one down. Two up, two down. Yes. That... Mm-hmm. Okay, kind of, that's what you do. You can change the loss. So typically you have two approaches, right? One that is kind of change things and let's hope for the best. You have the other one, which is kind of, okay, let's look back into the data and rework kind of the problem and see what we can understand. Most of us will change the losses and hope for the best, look whether things are converging or not, and look for the best. If not, then change the data and hope for the best. And at the very end, it's about hope, always hoping for the best. But essentially, in the problems that we address, these typically are inverse problems. They are highly nonlinear. They are quite likely non-convex. So essentially, non-unique solution, ill-posed problem, hidden system difficulties to characterize it, limited control on the learning, limited control during operation, limited interoperability, limited everything. So we basically pray that it will work. That's kind of a way to put it. So what I come to explain to you today is actually what we had been working now 2 years in this kind of theoretic approach, which kind of hope it's gonna be intuitive to you. I've done my best to try. So essentially the idea is this: could I start by solving a simpler problem? I do not mean by finding a simpler solution. I mean find another problem that is simpler. Then I'll try to solve it. Once I get the solution for that system, make it a little bit more complicated and find a solution, and make it a little bit more complicated and find a solution once again. And at the very end, hopefully, by learning from all those problems, finally reach a solution that is actually the solution to my problem. Could we actually do something like that? Essentially, that's what we do. The numbers, by the way, that are on the slide are just kind of a joke, okay? So we don't have any kind of Q equals 3/4, which means expressive model, nothing like that. But we do have this notion of an embedding parameter, which is Q, which at Q equals 0 means a simple problem that I know how to solve. At Q equals 1 means I do have the solution to my actual problem. What essentially means is that if you remember before, we had this M and K. We are building a family of problems. So we now still have M and K, but we also have Q and H. Now, H is essentially actually a control parameter, so no big deals. Now, what's Q? I've done my best, okay, with this non-animation, but I hope this can be understood. So essentially, when you search for your solution, you will pick a complexity for your problem, and you will just wait a number of steps, and that's all, okay? So essentially, your simulations live within this plane, okay? The more you wait, the larger the value of K. The more complex your system is, the larger the value of N, which is the option. Now, Q is essentially kind of this. So at Q equals 0, I have the exact same situation for a simple problem, at least one that I can control. Actually, it's not so simple. It's simply a surrogate problem that I can solve. Maybe it's not so simple, but essentially I can handle that. And then as Q increases, essentially I'm going to get to my actual problem and hopefully solve it. So what just happened is that we've built kind of a volume in here of all problems with their solutions that could be approached. That's essentially the idea. Now, kind of got it? Probably not. But you've done this before. I'll show you with an example in a few slides, so that you get the idea. The kind of formulation that we use is kind of like this, which is quite odd, but essentially this is the same problem that we had before, and now we have a bunch of things that appeared here, which is essentially is here a surrogate problem. This Q means Q equals 0, this is 1, this is 0, which basically means solve your simple linear problem. Typically it's going to be linear, that's why L. And where Q is larger, then go for the more complex one. Now, before I show you the example, comment I mentioned before, is this supposed to be solved with a standard math? Yes. So essentially, we are going to try to solve this using DDSP. The problem is we are going to differentiate with respect to the parameters, which you always do, but we are going to differentiate as well with respect to Q, so to the problems, which essentially means that in here, in your standard DDSP, I have spaces of numbers, so standard differentiation. In here, I've got operators. Essentially, in here, you have your standard derivatives, and in here, I've got the Frechet derivative. Have you heard about Frechet derivative? Also, essentially, is the way in which you differentiate an operator. By the way, if the operator happens to be a function, it's the standard math. Okay? If not, it has its issues. So I brought an example, which I hope you actually evaluated when you were kids, hopefully before you came to university, maybe not. So we'll check. Okay. How does a pendulum work? We all know the pendulum, right? So the string, the mass, okay, and it starts to oscillate. If you remember at some point in your life, someone told you, okay, if I put it this way, I would like to compute the period, right? Yes? And someone told you, okay, but let's not have a really large angle. Let's just stop and begin with a small one, right? Probably you don't remember, or hopefully no one actually gave you the ODEs that actually hold for this problem, assuming that this is non-frictionless and so on and so forth. But essentially, we have such an ODE like that, which is not nice to solve. If you recall your physics courses, essentially a small angle means approximated this sign by the angle, which is essentially that. And that's a simple problem. And it is a simple problem because we know that the solution for that ODE is a cosine. Problem is, let's be honest, if I've got my pendulum and I have my mass and it starts swinging, we all know that the period will change, right? Well, if I get this exact expression, the period cannot change. I don't know if you remember this from your school classes, but it doesn't change. So essentially, the model is not matching the actual reality. We could go with complex analysis discussing whether this phase should be the instant phase and then blah, blah, blah. Okay, good for you. Not interested at this point. I could do something simpler. I don't know if you remember your math, but essentially, if I go with this sign, I'll test something that was called the Maclaurin expansion. Remember that? Probably yes, but probably not. That basically means that the sign can be approximated. This is the first order approximation. What happens if I go with a third order approximation? This is my new problem. Can I solve it? Yes, I can. I know it's less easy, less sexy, but still I can solve it. Could this be a better problem than this one? Well, probably you haven't experienced this before, so I'll give you the solution in one slide. But essentially, yeah. Now, please note the thing that is coming up here. I am not changing my solution. I am changing my problem. And by adding more and more terms in here, I can have a better and a better approximation to my actual problem and therefore to the solution. Just in case, if any of you kind of feel like Euler today, essentially Euler did some math on this and found this kind of explicit direct model, which basically rewrote the equations into just not having this second order derivative, but just first order, which is kind of the intelligent mathematician guy did something smart to get a better result. I'll show you the result there. It's not necessarily the best. And mathematicians in the early 20th century came up with these real odd expressions. I don't know if anyone here knows what DOP means, but essentially this is a wrong-acute approximation. So kind of a long model to describe this. But so that you get an idea, a good problem for me is one that I can solve and is meaningful, right? It has to be meaningful. So this is exactly the solutions that you get when you actually run simulations on these different exact nonlinear system is just the pendulum, so you have the part sign and so on, and the math. So if you check the lines in here, essentially the small angle, the volume average, definitely has a different period, so definitely changes, because the other ones are changing. That kind of approach cannot. Now, if we compare actually the green and the purple one, these being basically third-year mathematician course, analysis course, so not so easy, whereas this is just a third-order approximation model, both of them work really nice. So I really have a really good approximation to the actual form of my system. Yeah. Once again, we have written a new problem, not just search for a new solution. By the way, I hope no one wants to see the math, but just the math. Anyways, it exists, okay? If someone wants to, I can share that, so glad to. But essentially, I guess you all know oscillators are everywhere, and essentially the kind of things that you do here at C4DM, and they are quite common. So essentially for me, when I am using this technology, or what we plan to do, we essentially consider the oscillator kind of as an input to something. Then we have kind of resonators, and we have a source of a body or something. We will get actually full audios in our system. And finally, we can validate the sound. But essentially, that's just a pendulum problem, right? Simple as that. If you actually have the right formulation of your problem, you might likely get better results than the standard ones. That's basically what I intend to do here. So that you have an idea, these surrogate problems, I didn't show the math so much, but the fact that you and me understand the problem doesn't mean that it is so easy to write down, okay? But nevertheless, still, can we actually apply this into the kind of things that you do here at C4DM? Essentially, yes, we can. At least that's what I'm trying, and I will continue to be trying until the end of August. Essentially, can we actually build a surrogate system of problems for the calculus-strong algorithm, which is actually thanks to Pablo here, because I hadn't thought about actually this exact application, but that's, well, yes, I can. I guess you all know about the calculus-strong algorithm, right? And if yes, kind of know, okay, essentially, you can produce sound that really sounds well, real well. Basically, to simulate plucked strings, essentially. That's a main situation where we use it. So can we actually use this to compute the parameters of such models, reframing the problem in this way? Essentially, yes, we can. The thing is, in the standard problem, we have the excitation. And in this case, we have some kind of oscillation there. So we need a surrogate problem to compute this oscillation. Then we have the propagation of sound, which also requires a surrogate problem as well. And finally, we've got a mapping, which you call the sinusoid or the waveform, actually. So we need an additional surrogate problem to formulate this thing on its own. So essentially, why the heck am I doing all of this? Because I can control the learning process, because I can control the operation process, I can control the procedure, and as well, I can actually control everything in this KSA model, well, extended actually, calculus-strong algorithm. So essentially, what can I bring here? What kind of things do I know about the signals? Well, I know that the kind of signals that are simulated essentially come from an acoustic guitar or a simulation of an acoustic guitar, which has implications. I can put that into my knowledge for formulating the surrogate problem. Why the heck should I log into waveforms in time if I want to focus on the pitch? There might be a good reason or might not, but there's kind of a knowledge that you have that I can put into my surrogate problem. The same happens about the model priors and so, because essentially the complexity of the problem, so the order of the approximation, that cube that you saw before for my sign, I can choose it because I want my problem to work, not because I know that that's the correct identification of the system. I have no clue of what's the best mathematical approximation. I just want to have one that is informed. I can have one that is informed based on this math. Additionally, this algorithm specifically does not treat noise quite well. I can actually handle noise. The last paper that we wrote on this theory was actually in electrical instrumentation and showing off how this can handle odd noise. By odd, I mean autoregressive noises and so on, which actually helps. And actually, we can add up constraints to our models. So essentially, this theory is just a way to reformulate stuff in kind of a slightly mathematical way. So to be honest with you, but one way that we are willing to test in different applications. So it's actually me here sharing this with you. And there's one of my PhD students actually in TU Berlin presenting exactly this same approximation to solve adjoint problems, basically for room reverberations. And actually, for those of you that may be attending DAFEX, you will meet him there. But essentially, he will be presenting this theory in there. In that case, he's not using the Carpel-Strong, he's actually using an equalizer, a parameterized equalizer. But anyways, for us, it's the same. I don't really understand much more. But I'm glad to learn and to learn more about your problems. Specifically, if you have this kind of prior knowledge that you do not know how to put into your program, glad to help. Or if you have kind of a willing to build interpretable stuff or controllable stuff, I don't really know which word I would prefer, but I will be glad to share with you. My goals here are basically, as I said, that's all. And final slide, just to say why this works. Essentially, by using this method, we divided by 2 the time that we require to train the same models that we were using before. So essentially, it will be calculating the same. So after 8 iterations, we add blah, 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 whatever value for the error. If I report my mathematical approximation which has several orders, then actually I can go for the 4 orders of magnitude below where I was quite quickly. Definitely not without a. Each iteration of this algorithm takes a little bit longer, not necessarily a lot, much, but essentially we check these things. Processing time goes actually increases this way compared to the other. But essentially, we are still at numbers that would definitely handle the problem. So essentially, compared to what is reported in the literature, we are already in here by 1,000 less time to compute, and we've got 4 orders of magnitude of a better result. Once again, and I yet don't understand anything really of what's going on except for the math. So glad to share with you my knowledge of how to do this if you have a problem where this might apply. And I guess that's all for me. Thank you for taking the patience to hear all about this. Any thoughts, ideas, problems you would like to share, I'm glad to hear. And by the way, there's notebooks to show up how this works, but it didn't seem like the occasion to share those with you. So I'll skip that. Kind of made sense to me. Thank you.